Hello, and welcome to a Let's Study on Programming Windows, 5th edition, by Charles Petzold, the definitive guide to Windows 32 API. We'll be starting at Chapter 1, Getting Started. This book shows you how to write programs that run under Microsoft Windows 98, Microsoft Windows NT 4.0, and Windows NT 5.0. Now, those were the operating systems at the time of this book, or later on, not changed with the newer editions of this book, but the Windows 30 API is still a part of Windows 10 and 11. These programs are written in the C programming language and use the native Windows Application Programming Interfaces, or APIs. As I'll discuss later in this chapter, this is not the only way to write programs that run under Windows. However, it is important to understand the Windows API regardless of what you will eventually use to write your code. As you probably know, Windows 98 is the latest incarnation of the graphical operating system that has become the de facto standard for IBM-compatible personal computers built around 32-bit Intel microprocessors such as the 486 and Pentium. Windows NT is the industrial-strength version of Windows that runs on PC compatibles as well as some RISC RISC reduced instruction set computing workstations. There are 3 prerequisites for using this book. First, you should be familiar with Windows 98 from a user's perspective. Having Windows 10, 11, pretty much any version of Windows, you'll be good to go. You cannot hope to write applications for Windows without understanding its user interface. For this reason, I suggest that you do your program development, as well as other work, on a Windows-based machine using Windows applications. Second, you should know C. If you don't know C, Windows programming is probably not a good place to start. I recommend that you learn C in a character mode environment such as that offered under the Windows 98 MS-DOS command prompt window. Windows programming sometimes involves aspects of C that don't show up much in character mode programming. In those cases, I'll devote some discussion to them, but for the most part, you should have a good working familiarity with the language, particularly with C structures and pointers. Some knowledge of the standard C runtime library is helpful, but not required. Third, you should have installed on your machine a 32-bit C compiler and development environment suitable for doing Windows programming. In this book, I'll be assuming that you are using Microsoft Visual C++ 6.0, which can be purchased separately or as a part of the Visual Studio 6.0 package. We'll be using Visual Studio 2022 Community Edition, which comes at no cost. That's it. I'm not going to assume that you have any experience at all programming for a graphical user interface such as Windows. The Windows environment. Windows hardly needs an introduction, yet it's easy to forget the C chain. Yet it's easy to forget the C changes. I feel like it's missing a sea of changes right here. Forget the sea of changes that Windows brought to Office and home desktop computing. Windows had a bumpy ride in its early years and was hardly destined to conquer the desktop market. A history of Windows. Soon after the introduction of the IBM PC in the fall of 1981, it became evident that the predominant operating system for the PC and compatibles would be MS-DOS, which originally stood for Microsoft Disk Operating System. MS-DOS was a minimally operating system. For the user, MS-DOS provided a command line interface to commands such as dir and type, and loaded application programs into memory for execution. For the application programmer, MS-DOS offered little more than a set of function calls for doing file input-output I/O for other tasks, in particular, writing text and sometimes graphics to the video display. Applications access the hardware of the PC directly. Due to memory and hardware constraints, sophisticated graphical environments were slow in coming to small computers. Apple Computer offered an alternative to character mode environments, wherein it released its ill-fated Lisa in January 1983, and then set a standard for graphical environments with the Macintosh in January of 1984. Despite the Mac's declining market share, it is still considered the standard against which other graphical environments are measured. All graphical environments, including the Macintosh and Windows, are indebted to the pioneering work done at the Xerox Palo Alto Research Center Park, beginning in the mid-1970s. Windows was announced by Microsoft Corporation in November 1983, post-Lisa but pre-Macintosh, and was released 2 years later in November 1985. Over the next 2 years, Microsoft Windows 1.0 was followed by several updates to support the international market and to provide drivers for additional video displays and printers. Windows 2.0 was released in November 1987. This version incorporated several changes to the user interface. The most significant of these changes involved the use of overlapping windows rather than the tiled windows found in Windows 1.0. Windows 2.0 also included enhancements to the keyboard and mouse interface, particularly for menus and dialog boxes. Up until this time, Windows required an Intel 8086 or 8088 microprocessor running in real mode to access 1 megabyte of memory. Windows 386, released shortly after Windows 2.0, used the virtual 86 mode of the Intel 386 microprocessor to Windows and multitask many DOS programs that directly access hardware. For symmetry, Windows 2.1 was renamed Windows/286. Windows 3.0 was introduced on May 22nd, 1990. The earlier Windows 286 and Windows 386 versions were merged into one product with this release. The big change in Windows 3.0 was the support of the 16-bit protected mode of Intel's 286, 386, and 486 microprocessors. This gave Windows and Windows applications access to 16 megabytes of memory. The Windows shell programs for running programs and maintaining files were completely revamped. Windows 3.0 was the first version of Windows to gain a foothold in the home and the office. Any history of Windows must also include a mention of OS/2, an alternative to DOS and Windows, that was originally developed by Microsoft in collaboration with IBM. OS2 1.0, character mode only, ran on Intel 286 or later microprocessors and was released in late 1987. The Graphical Presentation Manager (PM) came about with OS2 1.0 in October 1988. PM was originally supposed to be a protected mode version of Windows, but the graphical API was changed to such a degree that it proved difficult for software manufacturers to support both platforms. By September 1990, conflicts between IBM and Microsoft reached a peak and required that the two companies go their separate ways. IBM took over OS2, and Microsoft made it clear that Windows was the center of their strategy for operating systems. While OS2 still had some fervent admirers, it has not nearly approached the popularity of Windows. Microsoft Windows 3.1 was released in April 1992. Several significant features included the TrueType fonts technology, which brought scalable outline fonts to Windows, and multimedia, sound, and music, object linking and embedding (OLE), and standardized common dialog boxes. Windows 3.1 ran only in protected mode and required a 286 or 386 processor with at least 1 megabyte of memory. Windows NT, introduced in July 1993, was the first version of Windows to support the 32-bit mode of the 386, 486, and Pentium microprocessors. The programs that run under Windows NT have access to 32-bit flat address space and use a 32-bit instruction set. I'll have more to say about this address space a little later in this chapter. Windows NT was also designed to be portable to non-Intel processors, and it runs on several RISC-based workstations. Windows 95 was introduced in August 1995. Like Windows NT, Windows 95 also supported the 32-bit programming mode of the 386 and later microprocessors. Although it lacked some of the features of Windows NT, such as high security and portability to RISC machines, Windows 95 had the advantage of requiring fewer hardware resources. Windows 98 was released in June 1998 and has a number of enhancements, including performance improvements, better hardware support, and a close integration with the Internet and the World Wide Web. Oop. My motion sensor light went off. Aspects of Windows. Both Windows 98 and Windows NT are 32-bit preemptive multitasking and multi-threading graphical operating systems. Windows possesses a graphical user interface, GUI, sometimes also called a visual interface or graphical windowing environment. The concepts behind the GUI date from the mid-1970s with the work done at the Xerox PARC for machines such as the Alto and the Star, and for environments such as Smalltalk. This work was later brought into mainstream and popularized by Apple Computer and Microsoft. Although somewhat controversial for a while, it is now quite obvious that the GUI, in the words of Microsoft's Charles Simonyi, the single most important grand consensus of the personal computer industry. All GUIs make use of graphics on a bitmapped video display. Graphics provides better utilization of screen real estate, a visually rich environment, for conveying information and the possibility of a WYSIWYG. What you see is what you get. Video display of graphics and formatted text prepared for a printed document. In earlier days, the video display was used solely to echo text that the user typed using the keyboard. In a graphical user interface, the video display itself becomes a sort of user input. The video display shows various graphical objects in the form of icons and input devices such as buttons and scroll bars. Using the keyboard, or more directly, a pointing device such as a mouse, the user can directly manipulate these objects on the screen. Graphics objects can be dragged, buttons can be pushed, and scroll bars can be scrolled. The interaction between the user and the program thus becomes more intimate. Rather than the one-way cycle of information from the keyboard to the program to the video display, the user directly interacts with the objects on the display. Users no longer expected to spend long periods of time learning how to use the computer or mastering a new program. Windows helps because all applications have the same fundamental look and feel. The program occupies a window, usually a rectangular area on the screen. Each window is identified by a caption bar. Most programs' functions are initiated through the program's menus. A user can view the display of information too large to fit on a single screen by using scroll bars. Some menu items invoke dialog boxes into which the user enters additional information. One dialog box in particular that is used to open a file can be found in almost every large Windows program. This dialog box looks the same or nearly the same in all of these Windows programs, and it is almost always invoked from the same menu option. Once you know how to use one Windows program, you are in a good position to easily learn another. The menus and dialog boxes allow a user to experiment with a new program and explore its features. Most Windows programs have both a keyboard interface and a mouse interface, although most functions of Windows programs can be controlled through the keyboard. Using the mouse is often easier for many chores. From the programmer's perspective, the consistent user interface results from using the routines built into Windows for constructing menus and dialog boxes. All menus have the same keyboard and mouse interface because Windows, rather than the application program, handles this job. To facilitate the use of multiple programs and the exchange of information among them, Windows supports multitasking. Several Windows programs can be displayed and running at the same time. Each program occupies a window on the screen. The user can move the windows around on the screen, change their sizes, switch between different programs, and transfer data from one program to another. Because these windows look something like papers on a desktop, in the early days before the desk became dominated by the computer itself, of course, Windows is sometimes said to use a desktop metaphor. For the display of multiple programs. Earlier versions of Windows used a system of multitasking called non-preemptive. This meant that Windows did not use the system timer to slice processing time between the various programs running under the system. The programs themselves had to voluntarily give up control so that other programs could run. Under Windows NT and Windows 98, multitasking is preemptive and programs themselves can split into multiple threads of execution that seem to run concurrently. An operating system cannot implement multitasking without doing something about memory management. As new programs are started up and old ones terminate, Memory can become fragmented. The system must be able to consolidate free memory space. This requires the system to move blocks of code and data in memory. Even 1.0, even Windows 1.0, running on an 8088 microprocessor, was able to perform this type of memory management. Under real mode restrictions, this ability can only be regarded as an astonishing feat of software engineering. In Windows 1.0, the 640 kilobyte memory limit of the PC's architecture was effectively stretched without requiring any additional memory. But Microsoft didn't stop there. Windows 2.0 gave the Windows applications access to expanded memory (EMS), and Windows 3.0 ran in protected mode to give Windows applications access up to 16 megabytes of extended memory. Windows NT and Windows 98 blow away these old limits by being fully fledged 32-bit operating systems with flat memory space. Programs running in Windows can share routines that are located in other files called dynamic link libraries, which includes a mechanism to link the program with the routines in the dynamic link libraries at runtime. Windows itself is basically a set of dynamic link libraries. Windows is a graphical interface, and Windows programs can make full use of graphics and formatted text on both the video display and the printer. Graphical interface not only is more attractive in appearance, but also can impart a high level of information to the user. Programs written for Windows do not directly access the hardware of graphics display devices such as the screen and printer. Instead, Windows includes a graphics programming language called Graphics Device Interface, or GDI, that allows the easy display of graphics and formatted text. Windows virtualizes display hardware. A program written for Windows will run with any video board or any printer for which a Windows device driver is available. The program does not need to determine what type of device is attached to the system. Putting a device-independent graphics interface on the IBM PC was not an easy job for the developers of Windows. The PC design was based on the principle of open architecture. Third-party hardware manufacturers were encouraged to develop peripherals for the PC and have done so in great number. Although several standards have emerged, conventional MS-DOS programs for the PC had to individually support many different hardware configurations. It was fairly common for an MS-DOS word processing program to be sold with 1 or 2 disks of small files, each one supporting a particular printer. Windows programs do not require these drivers because the support is part of Windows. Dynamic linking. Essential to the workings of Windows is a concept known as dynamic linking. Windows provides a wealth of function calls that an application can take advantage of, mostly to implement its user interface and display text and graphics on the video display. These functions are implemented in dynamic link libraries, or DLLs. These are files with the extension .dll or sometimes .exe. They are mostly located in the Windows System subdirectory under Windows 98 and the Win32 System and Win32 System 32 subdirectories under Windows 90 NT. In the early days, the great bulk of Windows was implemented in just 3 dynamic link libraries. These represented the 3 main subsystems of Windows, which were referred to as kernel, user, and GDI. While the number of subsystems has proliferated in recent versions of Windows, most function calls that a typical Windows program makes will still fall in one of these 3 modules. Kernel which is currently implemented by the 16-bit kernel 386.exe and the 32-bit kernel 32.dll, handles all the stuff that an operating system kernel traditionally handles: memory management, file I/O, and tasking. User, implemented in the 16-bit user.exe and 32-bit user32.dll, refers to the user interface and implements the windowing logic. GDI, implemented in the 16-bit GDI.exe and the 32-bit GDI32.dll, is the graphics device interface, which allows a program to display text and graphics on the screen and printer. Windows 98 supports several thousand function calls that applications can use. Each function has a descriptive name, such as create window. This function, as you might guess, creates a window for your program. All the Windows functions that an application may use are declared in headers. In your Windows program, you use Windows function calls in generally the same way you use C library function calls, such as strlen. The primary difference is that the machine code for C library functions is linked into your program code, whereas the code for Windows function calls is located outside of your program in the DLLs. When you run a Windows program, it interfaces to Windows through a process called dynamic linking. A windows.exe file contains references to the various dynamic link libraries it uses and the functions therein. When a Windows program is loaded into memory, the calls in the program are resolved to point to the entries of the DLL functions, which are also loaded into memory if not already there. When you link Windows program to produce an executable file, you must link with special import libraries provided with your programming environment. These import libraries contain the dynamic link library names and reference information for all of Windows function calls. The linker uses this information to construct the table in the .exe file that Windows uses to resolve calls to Windows functions when loading the program. Windows programming options. To illustrate the various techniques of Windows programming, this book has lots of sample programs. These programs are written in C and use the native Windows APIs. I think of this approach as classical Windows programming. It is how we wrote programs for Windows 1.0 in 1985, and it remains a valid way of programming for Windows today. APIs and memory models. To a programmer, an operating system is defined by its API. An API encompasses all the function calls that an application program can make of an operating system, as well as definitions of associated data types and structures. In Windows, the API also implies a particular program architecture that we'll explore in the chapters ahead. Generally, the Windows API has remained quite consistent since Windows 1.0. A Windows programmer with experience in Windows 98 would find the source code for a Windows 1.0 program very familiar. One way the API has changed has been in enhancements. Windows 1.0 supported fewer than 450 function calls. Today, there are thousands. The biggest change in the Windows API and its syntax came about during the switch from a 16-bit architecture to a 32-bit architecture. Versions 1.0 through 3.1 of Windows used the so-called segmented memory mode of the 16-bit Intel 8086, 8080, and 286 microprocessors, a mode that was also supported for compatibility purposes in the 32-bit Intel microprocessors beginning with the 386. The microprocessor register size in this mode was 16 bits, and hence the C-int data type was also 16 bits wide. In the segmented memory model, memory addresses were formed from two components: a 16-bit segment pointer and a 16-bit offset pointer. From the programmer's perspective, this was quite messy. It involved differentiating between long or far pointers, which involved both a segment address and an offset address, and short or near pointers, which involved an offset address with an assumed segment address. Beginning in Windows NT in Windows 95, Windows supported a 32-bit flat memory model using the 32-bit modes of the 386, 486, and Pentium processors. The C-int data type was promoted to a 32-bit value. Programs written for 32-bit versions of Windows use a simple 32-bit pointer values that address a flat linear address space. The API for the 16-bit versions of Windows, Windows 1.0 through Windows 3.1, is now known as Win16. The API for the 32-bit versions of Windows, Windows 95, Windows 98, and all versions of Windows NT is now known as Win32. Many function calls remained the same in the translation from Windows 16 to Win32. But some needed to be enhanced. For example, graphics coordinate points changed from 16-bit values in Win16 to 32-bit values in Win32. Also, some Win16 function calls returned a two-dimensional coordinate point packed in a 32-bit integer. This was not possible in Win32, so new function calls were added that worked in a different way. All 32-bit versions of Windows supported both the Win16 API to ensure compatibility with old applications and the Win32 API to run new applications. Interesting enough, this works differently in Windows NT than in Windows 95 and Windows 98. In Windows NT, Win16 function calls go through a translation layer and are converted to Win32 function calls that are then processed by the operating system. In Windows 95 and Windows 98, the process is opposite to that. Win32 function calls go through a translation layer and are converted to Win16 function calls to be processed by the operating system. At one time, there were two other Windows API sets, at least in name. Win32S, S for subset, was an API that allowed programmers to write 32-bit applications that ran under Windows 3.1. This API supported only 32-bit versions of functions already supported by Win16. Also, the Windows 95 API, once called Windows 32C, for C for compatibility, but this term has been abandoned. At this time, Windows NT and Windows 98 are both considered to support the Win32 API. However, each operating system supports some features not supported by the other. Still, because the overlap is considerable, it's possible to write programs that run under both systems. Also, it is widely assumed that the two products will be merged at some time in the future, which it did. Language options. Using C and the native APIs is not the only way to write programs for Windows 98. However, this approach offers you the best performance, the most power, and the greatest versatility in exploiting the features of Windows. Executables are relatively small and don't require external libraries to run, except for the Windows DLL themselves, of course. Most importantly, becoming familiar with the API provides you with a deeper understanding of Windows internals, regardless of how you eventually write applications for Windows. Although I think that learning classical Windows programming is important for any Windows programmer, I don't necessarily recommend using C and the API for every Windows application. Many programmers, particularly those doing in-house corporate programming or those who do recreational programming at home, enjoy the ease of development environments such as Microsoft Visual Basic or Borderland Delphi, which incorporates an object-oriented dialect of Pascal. These environments allow a programmer to focus on the user interface of an application and associate with user interface objects. To learn Visual Basic, you might want to consult other Microsoft Pressbooks such as Learn Visual Basic Now, 1996, by Michael Halvorson. Among professional programmers, particularly those who write command applications, Microsoft Visual C++ with the Microsoft Foundation Class Library MFC has been a popular alternative in recent years. MFC encapsulates many of the messier aspects of Windows programming in a collection of C++ classes. Jeff Prosey's Programming Windows with MFC, 2nd edition, Microsoft Press 1999, provides tutorials on MFC. Most recently, the popularity of the Internet and the World Wide Web has given a big boost to Sun Microprocessor's Java, the processor-independent language inspired by C++ and incorporating a toolkit for writing graphical applications that will run on several operating system platforms. A good Microsoft Pressbook on Microsoft J++, Microsoft's Java development tool, is Programming Visual J++ 6.0, 1999, by Stefan R. Davis. Obviously, there's hardly any one right way to write applications for Windows. More than anything else, the nature of the application itself should probably dictate the tools. But learning the Windows API gives you vital insights into the workings of Windows that are essential regardless to what you end up using to actually do the coding. Windows is a complex system. Putting a programming layer on top of the API doesn't eliminate the complexity, it merely hides it. Sooner or later, that complexity is going to jump out and bite you in the leg. Knowing the API gives you a better chance at recovery. Any software layer on top of the native Windows API necessarily restricts you to a subset of full functionality. You might find, for example, that Visual Basic is ideal for your application, except that it doesn't allow you to do one or two essential chores. In that case, you'll have to use native API calls. The API defines the universe in which we, as Windows programmers, exist. No approach can be more powerful or more versatile than using this API directly. MFC is particularly problematic. While it simplifies some jobs immensely, such as OLE, I often find myself wrestling with other features, such as the document view architecture, to get them to work as I want. MFC has not been the Windows programming panica that many have hoped for, and few people would characterize it as a model of good object-oriented design. MFC programmers benefit greatly from understanding what's going on in class definitions that they use, and find themselves frequently consulting MFC source code. Understanding that source code is one of the benefits of learning the Windows API. The programming environment. In this book, I'll be assuming that you're running Windows Visual C++ 6.0, which comes in standard, professional, and enterprise editions, and the less expensive standard edition is fine for doing the programs in this book. Visual C++ is also part of Visual Studio 6.0. The Microsoft Visual C++ package includes more than a C compiler and other files and tools necessary to compile and link Windows programs. It also includes the Visual C++ Developer Studio, an environment in which you can edit your source code, interactively create resources such as icons or dialog boxes, and edit, compile, run, and debug your programs. If you're running Visual C++ 5.0, you might need to get updated header files and import libraries for Windows 98 and Windows NT 5.0. These are available at Microsoft's website. Go to http www.microsoft.com MSDN and choose with downloads, and then Platform SDK Software Development Kit. You'll be able to download and install the updated files and directories of your choice. To direct the Microsoft Developer Studio to look in these directories, choose Options from the Tools menu and then pick the Directories tab. The MSDN portion of the Microsoft URL above stands for Microsoft Developer Network. This is a program that provides developers with frequently updated CD-ROMs containing much of what they need to be on the cutting edge of Windows development. You'll probably want to investigate subscribing to MSDN to avoid frequent downloading from Microsoft's website. API documentation. This book is not a substitute for the official formal documentation of the Windows API. That documentation is no longer published in printed form. It is also available only via CD-ROM or the internet. When you install Visual C++ 6.0, you'll get an online help system that includes API documentation. You can get updates to that documentation by subscribing to MSDN or by using Microsoft's web-based online help system. Start by linking to www.microsoft.com MSDN and select MSDN Library Online. In Visual C++ 6.0, select the Contents item from the Help menu to invoke the MSDN window. The API documentation is organized in a tree structure hierarchy. Find this section labeled Platform SDK. All the documentation I'll be citing in this book is from this section. I'll show the location of documentation using the nested levels, starting with the Platform SDK separated by slashes. I know the Platform SDK looks like a small, obscure part of the total wealth of MSDN knowledge, but I assure you that it is essential core of Windows programming. For example, the documentation on how to use the mouse in your Windows programs, you can consult Platform SDK, User Interface Services, User Input, Mouse Input. I mentioned before that much of Windows is divided into kernel, user, and GDI subsystems. Kernel interfaces in Platform SDK, Windows-based services. The user interface functions are in Platform SDK, User Interface Services, and GDI is documented in Platform SDK, Graphics and Multimedia Services, those are GDI. Your first Windows program. Now it's time to do some coding. Let's begin by looking at a very short Windows program and, for comparison, a short character mode program. These will help us get oriented in using the development environment and going through the mechanics of creating and compiling a program. Character mode model. A favorite book among programmers, the C programming language. Sentence Hall, 1978 and 1988 by Brian W. Carnegie and Dennis M. Ritchie, affectionately referred to as KNR. This book. Well, this is a newer edition. We have a copy available to us and a Let's Study series in the workings. Chapter 1 of this book begins with a C program that displays the words Hello World. Here here's the program as it appears on page 6 of the first edition of the C programming language. We have a main function containing one statement of printf of hello world. Yes, once upon a time, C programmers used C runtime library functions such as printf without declaring them first. This is the 90s. We like to give our compilers a fighting chance to flag errors in our code. Here is a revised code from the second edition of KNR. We have hashtag include, in angled brackets, stdio.h. We have our main function and a single statement of printf hello world within. This program still isn't really as small as it seems. It will certainly compile and run just fine, but many programmers these days would prefer to explicitly indicate the return value of the main function, in which cases ANSI C dictates that the function actually returns a value. So then we have the hashtag include stdio.h within angle brackets. We have an int main function. We have two statements within with printf hello world and a return 0. We could make this even longer by including the arguments to main, but let's leave it at that, with an include statement, the program entry point, and a call to a runtime library function and a return statement. Here we have the Windows equivalent. The Windows equivalent to the Hello World program has exactly the same components as the character mode version. It has an include statement, a program entry point, a function call, and a return statement. Here is the program. We have hashtag include windows.h within angle brackets, and we have int win API, win main with arguments in h instance, an h instance, h previous instance, pstr, se command line, and an int I command show with as two statements. First statement being a message box, taking arguments of null, a hello Windows 98 text, a hello message text, and 0, and a return 0 statement. Before I begin dissecting this program, let's go through the mechanics of creating a program in the Visual C++ Developer Studio. To begin, select New from the File menu. So we're going to actually do this ourselves as well. I open up Visual Studio 2022. I create a new project. This will be an empty project of C++. Select Next. Give it a name. We'll give it Win32 underscore hello world in my learning library. Select create. Here we have our empty project. And if we right click in source files, hit add, new item, we can type in a hello msg.c. Not necessary, we could call it really anything. Ending with .c. We add this file. And then this is important. We have to go to our project settings. We right click our project settings, go to properties. We go down to linker, system. If we want to change the subsystem from console, we drop down to Windows. Hit apply, OK, and then we can begin editing our code. Let's give our code some information. This program displays hello world in a message box on screen. We have hashtag include windows.h in angle brackets. We have our int Win API, Win main. We have an H instance data type with the input parameter H instance. We have another H instance data type input, and this will be H prev instance. We have a pointer to a string, PSTR data type. This will be called SZ, CMD, line. And finally, we have an int I command show. We have a message box, function call, null with inputs null. We have the text, hello world. We have another text for our caption. Call this hello caption. And finally, we have 0. And then we, of course, return 0. And now, if we run this program, we have a message box come up with hello world and a caption, hello caption. And if we click OK, it closes and our application closes. To begin, select New from the File menu. We did this with a new project. In the new dialog box, pick the Projects tab, select Win32 Application, not necessary. We could start from a C++ standard, a C++ empty project, and then change the subsystem to be Windows. Type in the name of the project. We chose Win32_hello world. This will be a subdirectory of the directory indicated in the locations field. So yes, we chose our learning directory, and then this would create various subfolders of the name of the project. Platform sections should indicate Windows 32. We did that through the project settings subsystem to be Windows subsystem. A dialog box labeled Win32 application, step 1 of 1 appear, indicating that you want to create an empty project. Finish button. So what this book is talking about is, I think, closely related to the Windows Desktop Wizard template project. So if we go here and we click New Project and go Windows Desktop Wizard, next, we give it a name. I'll just leave it as Project 1. We hit Create. We should get a message, and now we can choose Desktop Application, Empty Project, and hit OK. So this is another way that we could do it. In which case, well, this seems a little bit more robust. Let's check. Let's add a main.c file and check our settings for differences from what we set up before. So if we go to Project 1, Project Settings, right-click, Properties, and System, we can see that it has already done this for us. We have the Windows subsystem model. So I don't think there's much difference between what we did before and what we did here, although it's probably more robust to use the Windows Desktop Wizard. Now if we go back and open our older project, Win32 Hello World. Open this. We have a hello message C file here. We're back to where we were. Structurally, the program we just wrote is identical to K&R Hello World program. The header file stdio has been replaced by windows.h. The entry main has been replaced with winmain. And the C runtime library printf has been replaced by the Windows API function message box. However, there is much in the program that is new, including several strange looking uppercase identifiers. Let's start at the top. The header files. Hello message.c, or in our case, hello, well, yeah, we named it the same, begins with a preprocessor directive that you'll find at the top of virtually every Windows program written in C. Hashtag include windows.h within angle brackets. Windows.h is a master include file that includes other Windows header files, some of which also include other header files. The most important and most basic of these header files are windef.h, basic type, which includes basic type definitions. wint.h brings in type definitions for Unicode support. winbase.h for kernel functions. winuser.h for user interface functions. And wingdi.h for graphics device interface functions. These header files define all the Windows data types, function calls, data structures, and constant identifiers. They are an important part of Windows documentation. You might find it convenient to use the Find in Files option from the Edit menu in the Visual C++ Developer Studio to search through these header files. You can also open the header files in the Developer Studio and examine them directly. Program entry point. Just as the entry point to a C program is the function main, the entry point to a Windows program is winmain, which also appears like this. We have int winmain with an h instance data type, h instance parameter 1. First parameter, we have h and another h instance data type, h prev instance parameter 2. Second parameter, we have a PSTR data type for our string, our null terminated string command line argument, and we have int I command show, finally ending off our input parameters for our winmain function. This entry point is documented in Platform SDK, User Interface Services, Windowing, Windows, Window Reference, Windows Functions. It is declared in winbase.h like so, line breaks and all. We have essentially what is the exact same winmain, but with a bunch of line breaks. Now, I will say this. It talks about that this is how it's defined in windows.h, but if we go up into our program, we can see that we have a warning message. This warning, C28251, says inconsistent annotation for winmain. This instance has no annotations. So if we go here, we peek the definition of Win API, go to SD call. How would I get to it?
Okay, so I finally found it. We have what is described as our Win API and how it is annotated in the winbase.h header file. I'll show you how I got there. So we have this Win API. We go to search. Well, actually, going off of the error message, we see that it is winbase.h in that header file location. I was able to use this search function, which I didn't ever use before, but now I will most likely very much use it. I'll go to code search and I'll type in winbase h, and we see we got the winbase.h file, header file. We select into that, and if we, well, Control F for Win API, go through our search results for that Win API for its definition. There's a lot of calls. Here we are. We have down here our wwin main, our Win API definition. Now, if we take this with us, copy it directly from the source, and bring it up here, and use this, we'll see that our warning message is now gone because it has the same annotations, these definitions, as in winbase.h header file. That is what we see down here in the book, where it has the line breaks and all. Well, winbase.h has even more than just line breaks. It has these annotations, these underscore ins and underscore in ops. So you'll notice I've made a couple minor changes. In hello msg.c, the third parameter is defined as an lpstr in winbase.h. I've made it to pstr. These two data types are both defined in WinNT. So taking from the definition in WinBase, you can see that it is in an lpwstr data type for the third parameter entered into the wmain, the winmain function. I have also changed two of the parameter names from the winmain declaration. Many Windows programs use a system called Hungarian notation for naming variables. This system involves prefacing the variable name with a short prefix that indicates the variable's data type. I'll discuss this concept more in Chapter 3. For now, just keep in mind that the prefix I stands for int, sz for string terminated with 0. The winmain function is declared as returning an int. The Win API identifier is defined in windef.h with the statement hashtag define win API __ stcall. This statement specifies a calling convention that involves how machine code is generated to place function call arguments on the stack. Most Windows function calls are declared as Win API. The first parameter to winmain is something called an instance handle. That is our H instance first parameter. In Windows programming, a handle is simply a number that an application uses to identify something. In this case, the handle uniquely identifies the program. It is required as an argument to some other Windows function calls. In early versions of Windows, when you ran the same program concurrently more than once, you created multiple instances of that program. All instances of the same program shared code and read-only memory, usually resources such as menu and dialog box templates. The program could determine if other instances of itself were running by checking the H previous instance parameter. It could then skip certain chores and move some data from the previous instance into its own data area. In the 32-bit versions of Windows, this concept has been abandoned. The second parameter to WinMain is always null, defined as 0. The third parameter to WinMain is the command line used to run the program. Some Windows applications use this to load a file into memory when the program is started. The fourth parameter to WinMain indicates how the program should be initially displayed, either normally or maximized to fill the window, or minimized to be displayed in the task list bar. We'll see how to use this parameter and used in Chapter 3. We'll see how this parameter is used in Chapter 3. The message box function. The message box function is designed to display short messages. The little window that message box displays is actually considered to be a dialog box, although not one with a lot of versatility. The first argument to message box is normally a window handle. We'll see what this means in Chapter 3. The second argument is the text string that appears in the body of the message box. And the third argument is the text string that appears in the caption bar of the message box. In hello message.c, each of these text strings is enclosed in a text macro, in capital TEXT. You don't normally have to enclose all character strings in the text macro, but it's a good idea if you want to be ready to convert your programs to the Unicode character set. I'll discuss this more in detail in Chapter 2. The fourth argument to message box can be a combination of constants beginning with the prefix NB_, that are defined in WinUser.h. You can pick one constant from the first set to indicate what buttons you wish to appear in the dialog box. We have a list here. We have OK, OK cancel, abort, retry, ignore, yes, no, cancel, yes, no, retry, cancel. When you set fourth arguments 0 to hello MSG, only the OK button appears. You can use the C OR operator to combine one, so that the bitwise operator OR, shown with the vertical line operator, to combine one of the constants shown above with a constant that indicates which of the buttons is the default. We have a new list: def button 1, def button 2, def button 3, def button 4. You can also use a constant that indicates the appearance of an icon in the message box. We have 4 choices. We have an icon hand, an icon question, an icon exclamation, and an icon asterisk. Some of these icons have alternative names: icon warning, icon error, icon warning for icon explanation, icon error for icon hand, icon information for icon asterisk, icon stop for icon hand. There are a few other MB_ constants, but you can consult the header file yourself or the documentation in Platform SDK, User Interface Services, Windowing, Dialog Boxes, Dialog Box Reference, Dialog Box Functions. In this program, the message box function returns the value 1, but it's more proper to say that it returns ID OK, which is defined in WinUser.h as equaling 1. Depending on the other buttons present in the message box, the message box function can also return ID yes, ID no, ID cancel, ID abort, ID retry, or ID ignore. Is this little Windows program really the equivalent of KNR Hello World program? Well, you might think not, because the message box function does really have all the potential formatting power of the printf function in Hello World. But we'll see in the next chapter how to write a version of message box that does printf-like formatting. compile, link, and run. When you're ready to compile hello message, you can select build hello message.exe from the build menu or press F7, or select the build icon from the build toolbar. So we just selected the local Windows debugger play button at the top to build and run our program. The appearance of this icon is shown in the build menu. If the build toolbar is not currently displayed, you can choose Customize from the Tools menu and select the Toolbars tab, pick Build or Build Minibar. Alternatively, you can select Execute hello message.exe from the Build menu or press Ctrl F5 or click the Execute Program icon, which looks like a red exclamation point from the Build toolbar. You'll get a message box asking you if you want to build the program. As normal, during the compile stage, the compiler generates an .obj object file from the C source code file. During the link stage, the linker combines the .obj file with the .lib library files to create the .exe executable file. You can see a list of these library files by selecting Settings from the Project tab and clicking the Link tab. In particular, you'll notice kernel32lib, user32lib, and GDI32lib. Let's check that. So we right-click on the project properties, go to Linker, in the linker, maybe input, additional dependencies, edit these, nope. I'm not seeing it, but I believe it's there. So let's do debug, active 64, input. Maybe it's in the core library dependencies. I wish I knew what this meant. These macros? Ah, I see these macros. Additional core library dependencies. So A, B, C. Core library dependencies of our subsystem system Windows 32, or just so the Windows subsystem. We can see that we have these: the kernel32.lib, win32.lib, and gdi32.lib, as well as a few others. Along with, well, yep, that's all that's in the book. Awesome. So that book, even written in 1999, 26 years ago, is still correct. These are import libraries for the free major Windows subsystems. They contain the dynamic link library names and reference information that is bound into the .exe file. Windows uses this information to resolve calls from the program to functions in the kernel 32 DLL, user32 DLL, and GDI 32.dll dynamic link libraries. In the Visual C++ Developer Studio, you can compile and link the program in different configurations. By default, these are called debug and release. The executable files are stored in subdirectories of these names. In the debug configuration, information is added to the .exe file that assists in debugging the program and in tracing through the program source code. If you prefer working on the command line, the companion CD-ROM contains .mak makefiles for all the sample programs. You can tell the Developer Studio to generate makefiles by choosing options from the Tools menu and selecting the Build tab. There's a checkbox to check you'll need to run vcvar s32.bat located in the bin subdirectory of the developer studio to set environment variables. To execute the make file from the command line, changes to the hello msg directory and execute and make /f hello message.mak cfg equals ms hello message dash win32 debug, or in make /f hello message.make config equals msg dash win32 release. You can then run the .exe file from the command line by typing debug /msg or release /msg. I have made one change to the default debug configuration in the project files on the companion CD-ROM for this book. In the project settings dialog box, after selecting the C tab in the preprocessor definitions field, I have defined in the identifier Unicode. I'll have much more to say about this in the next chapter. I'll close it off here for this episode of a Let's Study of Programming Windows, 5th edition by Charles Petzold, the definitive guide to the Win32 API. And we have read through chapter 1 and have completed writing our first Windows operating system program. Thank you for watching. Stay tuned for next episode on chapter 2, an introduction to Unicode. Thank you and have a good rest of your day.